Hello, welcome to the FOSS channel for self-paced tutorials on Internet of Things. This video illustrates translation operations for image transformations using basic OpenCV functions. Image transformation using only translation shifts the image along the coordinate axes. For 2D images, the shift occurs along the X and Y axes. Pure translation does not change the scale of the image, nor does it rotate the image. The translation values can be represented as a vector which is applied to all points in the image. If the translation value moves the image along a coordinate axis in one direction, then the negative value will move the image in the opposite direction. Image translation may appear to be simple. It is, however, a fundamental building block for many complex graphics applications. Some of the key disciplines for the application of image translation are gaming, some of the other disciplines are animation, user interface, image processing, video editing, virtual and augmented reality. While the focus in the current tutorial is on pure translation without scaling or rotation or shearing, in practical applications, the other fundamental operations that were mentioned in the introductory tutorial on scaling can be combined to create complex effects. Image translation is a fundamental concept in game development. It serves as a core operation in many popular games for gameplay mechanics and visual effects. Here are a few ways translation is applied in gaming. Character movement, moving characters across the game world. Object interaction, shifting objects like crates or power-ups. The movement of Tetris game pieces, also known as tetronyms, is the simplest example of translation by image transformation. There is an option to perform rotation in Tetris, but that operation will be a subject of a later tutorial. Camera movement, simulating camera panning or following a character. We will examine these operations in the next few slides. Basic movement, translating character sprites or 3D models across the game world. Let's take a look at how to translate sprites across the screen. So I've prepared a very simple elementary demonstration for you to understand how we can move sprites, which are characters, across the screen based on responses from either the keyboard or a gamepad controller. So in this simple example, if we press the left arrow, then the sprite will move to the left. We're reducing the speed by negative there. And if we press the right arrow, it'll go to the right. If we press the up arrow, remember the coordinate system 0, 0 is the top left-hand corner. So if we press the up arrow, it's going to go down, and then plus is for the down arrow. So a very, very simple program to show a sprite, and the sprite is essentially just a disk, a button, a yellow button along the lines of, in the old days, we used to call a Pac-Man game. And this is essentially how a Pac-Man worked. So let's run this. So we run it, and it's going to go into the Windows game. And by the way, we're using Pygame just to illustrate this. And so up comes the window, and very shortly you'll see the sprite right in the center of the screen. If I press the right arrow, it goes to the right. If I press the left arrow, it goes to the left. If I press the up arrow, it goes up and then down. All right. So hopefully, this gives you an idea how we can use the keyboard to perform what are essentially translation movements, where the rotation or the scale of the object does not change. It's just the X and Y position of the object changes. And once again, I can just show you that pressing the key on the right makes it go to the right. Pressing the key, arrow key on the left makes it go left and up and down. And you could just have another key or an action, so that as soon as we go up, we orient it in that direction, rotation, which will be the next video tutorial, by the way, where I'll discuss rotation. But if we had the background grid of a checkerboard, we could move this object around on the checkerboard and make sure that it could gobble up the ghosts or whatever else they call in the Pac-Man game. So interesting, very simple, but as you'll see as I show you more examples of translation, it is really a very basic fundamental concept of 2D games. Platforming. Precise control over character jumps, climbs, and ledge grabs requires accurate translation. For the next demonstration, to illustrate controlling jumps, climbs, and ledge grabs, I just resorted to a very simple game called X-Jump under Linux. And here we have 4 floors, and of course we're a beginner. Now please pardon me, I'm not a gamer, so I'll probably not be able to make any scores meaningful here, but I just want to illustrate the concept of moving vertically with translation movements and then moving horizontally with the same object to either horizontally. So let's get the game started. And here we have the object in here, so we just move up, and then we move up. See, you can see how you can move, and now the game is over. So let's try it one more time, just to give you a concept. And so just move it to the right with the keyboard, and there we go, and the game is over. So essentially, I mean, it's all of you might laugh at me and my game skills, but it just shows that translation is just simply moving the sprite across the screen, and then hopefully you have the underlying software to control the calculations and the collision detections and all, and to rank your score, which is a separate topic. Has nothing to do. The collision detection, of course, is part of graphics, but keeping the score and etc. is outside the scope of this tutorial. So one last time, let's see if I can do something meaningful here. And since I'm not using, there you go. So hardly scored anything. In addition to just the basic translation movement in X and Y, we can control the movement by using some physics. The simple example would be applying gravity. And the best way to illustrate that is to use a simple game of a bouncing ball. So if I click on this, you can see the balls are bouncing, and they bounce based on the gravity rules that you set up. So once I click, there is no further action required. The ball just bounces on the basis of the physical properties of the ball and the laws of gravity. Animations. Combining translation with other transformations like scaling and rotation to create fluid animations for walking, running, and attacking. In our final demonstration for this slide related to character movement, I'd like to show you a little bit about running, walking, and attacking using a Space Invader type game. So here are some instructions for running it. I press the S key to start it, and down here, and then I can just, you can see all the objects that are being moving around. They're pure translation movements for three things: the target, the attacking style, and also the player at the bottom is moving in constrained to one direction. So hopefully I've given you some ideas on using sprites with translation, which is the basic or fundamental movement for sprites, how to create very simple games, of course, by applying a few other considerations like a physics engine. In object interaction, during item pickup, items are translated towards a player. That is, the objects are moved towards or away from the player. During object movement, the trajectory of game elements is simulated with or without rotation. In scene interactions, objects are moved from one position to another. Let us do another simple demonstration of object movement by simulating the trajectory of game elements. So once again, we'll go ahead and work on a game here. And so as you can see, I can move the object out of the way, and so it'll dodge the asteroids that are coming. But essentially, you can see all the objects that are coming are not scaled or rotated. And so I have to move it out of the way. The object is not moving, and the trajectory is following basic principles of physics. So yet again, another very simple example of how translation is applied in some of these old arcade games. Here is another one that you might find useful. I certainly don't, because I don't play these games, but this is going to take a while to launch. But it's a character game, and it's more of an arcade game that you can see. It's called Wolf 5, and we can turn on, and different elements are shown here. And as we move around, the objects move. So I hope you get the idea of how translation is so important in arcade-style games. In camera control, we have panning, just translating the camera view horizontally or vertically. We have following, moving the camera to follow a character or object. And we have zooming, combining translation with scaling to create a zooming effect. Some basic examples of translation in animation are keyframe, character, and object. In keyframe animation, the translation of objects is performed between keyframes to create motion. In character movement, the character is animated using translation by walking, running, or jumping. In object motion, translation is used to create animations for moving items like cars, planes, or other mechanical objects. For user interface, the translation examples are dragging, scrolling, and window management. In dragging and dropping, translation moves elements on the screen. In scrolling, translation results in content moving horizontally or vertically within a scrollable area. In window management, translation provides positioning and resizing of windows. These operations are fundamental for the smooth operation of any productive graphical user interface. Most of us do not even blink an eye on the underlying image translation at work to support these diverse variety of user interfaces. And needless to add, the pioneering work at the Xerox Palo Alto Research Center, PARC, is merely a footnote in history, since the foundational work is embodied in Microsoft Windows, Apple OS, and Linux X Windows or Wayland. The underlying ingredients of the beverage are the same, irrespective of your preference for a particular flavor. In image processing, some of the applications for translation during image transformation may be applied to image registration, object tracking, and image stitching. In image registration, aligning multiple images by translating one or more of them. Of course, the images may require other transformation operations prior to the image translation step. In object tracking, following the movement of objects in a video sequence. This is very common in sports TV shows where replays often use moving boxes or circles to portray a commentator's viewpoints. Sometimes we use an overlay element, a rectangular or elliptical box, to illustrate the tracking of the object. Or better still, we implicitly use the technique to keep the object being tracked in the center of the viewing frame. In image stitching, combining multiple images by translating and overlapping them. Edge matching and boundary alignment is one of the examples of this operation that was common in geographic information systems, GIS, work over 40 years ago. Again, image translation was just one transformation operation in the process workflow. Some of the common uses of image translation in video editing are panning, picture-in-picture, and video effects. In panning, there is simulation of camera movements. In picture-in-picture, there is positioning of smaller video windows within a main video frame at various positions. In video effects, there is creation of effects like dissolving or fading the image over another image. Some examples of image translation in virtual and augmented reality are character movement, object interaction, and camera movement. In object placement, there is positioning of virtual objects in the real world. In user interaction, there is movement of virtual objects based on user input. In environment simulation, there is creation of dynamic environments with moving elements. Please pardon me if I had to illustrate each of the major cases where image translation plays an important part. This tutorial would have to be extended unduly. I hope you get the basic idea and allow me to summarize the underlying calculation principles. Let us take a quick look at the translation equations. Let us assume that each pixel in an image is a point. The point generalized as P for this discussion lies in space as represented by coordinate values x, y, and z in the respective coordinate axes. The linear movement with no scaling or rotation is expressed with directional movement values t sub x, t sub y, and t sub z in the respective coordinate axes. This is represented as the matrix T with the translation values in the fourth column. The new point, expressed as P prime, is computed by multiplying the matrices P and T. We expand the results of the multiplication matrix for a point in 2 dimensions. The equations can be represented as x prime is equal to x plus t sub x and y prime is equal to y plus t sub y. In this example, our point P is represented as vector in 3D space with the x, y, and z coordinate values as 2, 3, and 4 respectively. The fourth element is always 1 to ensure the use of homogeneous matrix operations. Let us assume that the translation vector is composed with t sub x equal to 1, t sub y equal to -2, and t sub z equal to 3. These values represent the movement of the point P along the designated coordinate axes. The translation matrix T is a 4 by 4 matrix with the translation values in the fourth column. The diagonal column elements are all set to 1 since there are no other transformation operations under consideration. The remaining elements are 0. The product of the matrices P times T generates the values for the new point P prime. Each element for x, y, and z is simply the sum of the original value plus the translation value. Let us review the simplified calculations again. This time, it will be for 3D space. The equations on this slide illustrate the result of matrix multiplication. In dealing with 2D images, we can drop the z element from further consideration. The new x-coordinate value is the sum of the original x-coordinate value plus the horizontal translation factor. Similarly, the new y-coordinate value is the sum of the original y-coordinate value plus the vertical translation factor. Let us perform another set of calculations using basic arithmetic if no other image transformations are at work. We have 3 sets of points at 0, 0, 1, 1, and 0, 2. We will move these points by 2 units horizontally and 1 unit vertically. The numerical values on the new points are shown on the 2 columns on the right of the table. The new points are 2, 1, 3, 2, and 2, 3. We added the value 2 to the x-coordinates of the original points and the value 1 to the y-coordinates to derive the new coordinates of the point. Although these are some very basic equations in image transformations, translation alone does play a big part in rendering images, as we have discussed in the previous slides. Of course, in combination with scaling and rotation, which we will discuss in the next tutorial, the Euclidean transformations are very important elements in computer graphics. Since there is no dedicated function in OpenCV to perform translation, we use the warp affine function to perform the same operation. Of course, warp affine can perform many other image transformations, but let us limit our discussion in this tutorial to image translation only. For translation, the affine transformation matrix is a 2 by 3 matrix. The size of the output image and the type is the same as that for the input image. The flags can be a combination of interpolation methods. We covered the basic interpolation methods in our scaling tutorial. Border mode represents the pixel extrapolation method. If the border mode is equal to border underbar transparent, then the pixels in the output image corresponding to the outliers in the source image are not modified by the processing in the warp affine function. Border value is applicable when there is a constant border. The warp affine function effectively applies the translation transformation to each pixel in the image. The affine transformation matrix is a powerful tool for various geometric operations. Understanding the mathematical basis can help you customize and optimize image transformations. By understanding the underlying mathematics, you can better grasp how warp affine function works and apply it effectively in your computer vision projects. Let us look at the parameters for the warp affine function. Image registration, aligning multiple images by translating one or more of them. Of course, the images may require other transformation operations prior to the image translation step. Object tracking, following the movement of objects in a video sequence. This is very common in sports TV shows where replays often use moving boxes or circles to portray a commentator's viewpoints. Sometimes we use an overlay element, a rectangular or elliptical box, to illustrate the tracking of the object. Or better still, we implicitly use the technique to keep the object being tracked in the center of the viewing frame. Image stitching, combining multiple images by translating and overlapping them. Edge matching and boundary alignment is one set of examples of this operation that was common in geographic information systems. Again, image translation was just one transformation operation in the process workflow. An affine transformation is a linear transformation followed by a translation. If the linear transformation is a unit matrix, then the transformation will be a basic translation operation. Let the original point be represented by a vector xy. The translation in x and y are tx and ty respectively. To represent points in 2D space for use in matrix multiplication, we use homogeneous coordinates. This involves adding a third coordinate, usually 1, to each point. The affine transformation matrix is a 2 by 3 matrix labeled as M in the slide. The new point is calculated by multiplying the affine transformation matrix with the homogeneous coordinates of each pixel in the image. The result of the multiplication gives the new coordinates of the pixel in the transformed image. In OpenCV's warp affine function, the function iterates over each pixel in the input image. For each pixel, it converts its coordinates to homogeneous coordinates. It multiplies the coordinates by the affine transformation function. The resulting coordinates are used to find the corresponding pixel in the output image. The pixel value from the input image is copied to the corresponding pixel in the output image. Here is a code snippet to illustrate the use of the warp affine function. We load an image using the cv2.imRead function. We define the translation factors tx and ty. We create the affine transformation matrix M. We apply the transformation using cv2.warp_affine. The output image DST will be the original image translated by tx pixels horizontally and ty pixels vertically. We display the original and translated images. By adjusting the tx and ty values, you can control the amount of translation applied to the image. Let us view a simple demonstration of the warp affine function. Here is a simple way to construct a helper function to perform only the translation operation. Since we need only tx and ty to be applied to the image, we do not encumber the mainline code with setting up the homogeneous transformation matrix, where the warp affine method is invoked. We simply pass three parameters to the helper function: the image to be translated along the axial directions, and the two corresponding movement values as tx and ty. Image translation may appear to be simple. It is, however, a fundamental building block for many complex graphics applications. Some of the key disciplines for the application of image translation are gaming, animation, user interface, image processing, video editing, virtual and augmented reality. While the focus in the current tutorial is on pure translation without scaling or rotation or shearing, in practical applications, the other fundamental operations that were mentioned in the introductory tutorial on scaling can be combined to create complex effects. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from OpenCV for many examples on basic concepts, and from free open source software, FOSS, for the three integrated development environments: IDE from PyCharm for Python, KDevelop for C++, and Google for Android Studio. Also, the backbone for the presentation of this video is from Inkscape, OBS Studio, Kdenlive, LibreOffice, and of course, Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.